Hello, this lecture will cover pages 109 through 111 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Additional Analysis Techniques, Chapter 5D, Norton's Theorem. If you remember, over the past 3 lectures or so, we're in chapter number 5, and I wanted to discuss 5 different analytical techniques that you'll use through the remainder of this course. Linearity was one of them. Superposition was another. Thevenin's theorem. We have to cover Norton's theorem and maximum power transfer. Looking at Norton's theorem right now, it's on page number 109. Norton's theorem is somewhat related to Thevenin's theorem, and I'll illustrate that as we go through this. Norton's theorem states that any two-terminal linear bilateral network can be replaced by an equivalent circuit comprised of a constant current source equal to the short circuit current developed when the terminals of the original circuit are shorted in parallel with the resistance or impedance measured looking back into the original circuit with the load removed. It has similarities to Thevenin's theorem. Remember, with Thevenin's theorem, we replaced an equivalent circuit with a voltage source and a series resistance called a Thevenin resistance and a Thevenin voltage. Here, we're replacing the equivalent circuit with a current source and a parallel resistance. If you take a look, the Norton current is going to be the short circuit current between the terminals of the original circuit. If you remember, Thevenin's theorem was the open circuit voltage, but Norton's the Thevenin voltage was the open circuit voltage, and the Norton current is going to be the short circuit current. Here's the equivalent circuit for a Norton equivalent. Notice it has the current source and it has a parallel resistor. This is the only form of the Norton equivalent circuit. The resistor isn't up here. The resistor is always in parallel, and you have a current source in parallel with the resistor. If you remember the Thevenin equivalent, it looked like this. And we had source conversions that took it from here to here and took it from here to here. You didn't know you were doing that at the beginning of the chapter, but if you remember, if you have a Norton circuit, if you had this current source, we could always go back to this equivalent voltage source by calculating that open circuit voltage there. Well, that open circuit voltage was just the current times the resistance. This current times the resistance. And that's all it is when you go from here to here and you want to take this circuit back to a Thevenin equivalent. The open circuit voltage of this circuit is the Norton current times the Norton resistance. And the Norton resistance just comes up in series. Same resistor comes up in series with the Thevenin voltage. What if you have the Thevenin equivalent circuit and you want to get a Norton equivalent circuit? Well, it's just the short circuit current between here and here. You short that out, just like I showed you here in the beginning of the chapter. You calculate that current, which is E Thevenin divided by R Thevenin. That becomes the value of this current, Norton current. And you bring that resistor down in parallel. So you should be able to go from here to here or here to here. We've already covered it. But let's get back up to Norton's theorem. Norton's theorem, you're calculating short circuit current. That's basically what you have to remember. In Thevenin's theorem, you're calculating open circuit voltage. You use the same procedure pretty much as I gave you for Thevenin's theorem. So let's take a look at a problem here. This problem's on page 110. Example 1. Here I have a circuit. It says find the Norton equivalent circuit between terminals A and B. They're giving you terminals A and B. And notice it's just not one resistor. It's a resistor and it's a voltage source. So the first thing you do, like it says in the procedure, is you remove the component or components. You remove it and you redraw the circuit. So I'm just removing these, labeling the terminals. This circuit is the same as this one up here with these removed. And then you reduce all the sources to 0. And you look back into the circuit and you find R Norton, just like you would find R Thevenin. You find R Norton and you find R Thevenin the same way. That step is the same. Well, how do you reduce this current source to 0? You open it. You do not short current sources when you reduce them to 0. You open it. So with this open, you just have this in the circuit and you have this in the circuit. Looking back in, do you see you have 27 in parallel with 27? The Norton resistance is 13.5 ohms. You put that in the circuit. Here it is. Now you want to go back and you want to calculate the Norton current. What's the Norton current here? It's the short circuit current. You draw a straight line between here and you calculate the current through there. Well, as soon as you draw a line and short this point to this point, this 27 ohm resistor goes out of the circuit. Because if you're current flowing here, you're not going to go in this through this element when you can go through the short circuit. So basically it takes the 27 ohms out. And if you want to find out what this short circuit current is, which is the Norton current, it's just the current divider rule. It's the total current entering the node times the opposite resistor, which is the 23 ohms, divided by the sum of the resistors, which is 23 plus 4. Again, you don't add in the 27. It's shorted out here. And you get your Norton current of 15.33 amperes, and you write it in. Here is the Norton equivalent circuit. And then you place the 47 ohm and the 180 volt source in between terminals A and B, and now you can calculate currents, voltage, powers. It simplifies this circuit considerably, because this circuit right here to the left of my pencil, that Norton equivalent circuit with that Norton current and that Norton resistance, is the same circuit looking back in from terminals A and B with this removed. Now on an exam, I may ask you to find the Thevenin equivalent circuit, which you're finding open circuit voltage. Or I may ask you to find the Norton equivalent circuit, which you're finding a short circuit current. But if I don't ask you how to do that, and ask you to find the Norton equivalent circuit, you could always just find the Thevenin equivalent circuit and then do a source conversion back to the Norton. Because if you Theveninize this circuit between terminals A and B, which would be a good exercise, you get this for an answer. You get this. And some students would do that and then do a source conversion between here by shorting this out, finding that current and putting it here, and bringing that resistor in parallel and putting it here. So how did I end up with this Thevenin circuit from this? Or between terminals A and B is an open circuit. The open circuit voltage between here and here is that current times that resistance. That's how I get 206.96 volts. And I just moved that parallel resistance up in series. I converted from this current source to this voltage source. On page 111, I want to mention Thevenin and Norton circuits containing dependent sources. Very important, because most of your homework problems are going to have dependent sources in them. In these types of circuits, which you have dependent sources, you cannot calculate R Thevenin as we had in step 2 of the previous examples. You must calculate R Thevenin by first calculating both the open circuit voltage and the short circuit current, and then forming that ratio to find the Thevenin resistance. In this course, it's the only way you're going to know how to find the Thevenin resistance. So basically what you're doing is you're calculating the open circuit voltage, which is the Thevenin voltage, and you're calculating the short circuit current, which is the Norton current. And you're dividing the current into the voltage, and you're getting that Thevenin resistance. By the way, finding Thevenin resistance this way works for all circuits. Even if all the circuits have independent sources in them, you could still go through this double procedure to find R Thevenin, but it's a lot easier just to reduce them to 0. But you can't reduce them to 0. Let me show you what I mean here, because this is what you're going to have for homework. When you see problems like this, when you see a problem like this, See if we can't get that on. When you see a problem like this, it has a dependent source. It's a voltage controlled voltage source. As soon as you see that, you have to calculate. You're trying to find I/O here using Thevenin's theorem, don't forget. So you remove this element and you label that terminal as A and that terminal B. And then you have to find the open circuit voltage between this point and this point. In other words, find the voltage at that node with respect to ground. And then find the short circuit current. Once you find both of those, then and only then can you find R Thevenin. Problem like this, same thing. Dependent source, you have to find, here's where they want you to find the output voltage across this resistor. You remove this resistor. You remove that resistor because that's where you're trying to find the voltage across. You make that the load resistor. You label this terminal A and this terminal B. You find the open circuit voltage. You find a short circuit current. I don't care if you use loop analysis, nodal analysis, superposition. I mean, we did a lot of these problems. I think it was in chapter 3 where we use loop and nodal analysis to find that. Same thing down here. Same thing down here. These are homework problems. So whenever you're looking at a problem and they ask you to find a Thevenin equivalent circuit and you see a dependent source in it, the first thing you ought to say is, damn, I have two problems to work out. Because you have to find the Thevenin voltage and you have to find the Norton current. That's an important concept. In the book, they make a big deal out of that. It's when we were talking about how you handle circuits, how you handle Thevenin and Norton circuits containing dependent sources. Remember, this is important. I tried to explain it here. And that concludes this lecture.